Okay, so chapters 5 and 6 that we just barely covered have been all about chemical reactions. So, how to predict products, how we classify chemical reactions, how we balance them, how we do math with them and convert from one thing to another. But chapter 7 is about why. Why do chemical reactions occur in the first place? Because we're scientists, and that's what we do, is we ask why. Why? Once we determine something interesting, like classifying chemical reactions, then we ask why. Okay, so before we answer this question, we need to understand something about energy. Because as it really turns out, all the substances in the world and the universe, all the compounds and elements and atoms, want to be in their lowest energy state. You could think of them as kind of being lazy. Like if you had a choice between laying on the couch and running a marathon, you'd probably lay on a couch unless you're one of those crazy marathoner people. And most atoms and elements are not. They just rather lay on the couch. So we have to talk about energy. We've got two forms of energy in the world. We have kinetic energy and we have potential energy. And kinetic energy is the energy of motion. Anything that's moving has kinetic energy. So a moving car has kinetic energy, and if that car stopped moving, that energy would have to be transferred to something else, like the brakes or the wall of the building that it hit, kind of a thing. A potential energy is energy that is stored. It's not being acted on at the moment, but it could potentially be acted on. So for instance, a battery has potential energy because it might not be releasing that energy right now, but if you hook it up to a device, then that device could harvest that energy and could use it. Really common explanation of this would be something like a ball at the top of a hill that's just sitting there has potential energy because it could roll down, but it hasn't started yet. Somebody gives it a tiny push, then as it rolls down the hill, it has kinetic energy, or the energy of motion, until it continues until it stops, essentially. So potential energy at the top of the hill, kinetic energy as it rolls down the hill. You guys following me here? Excellent. Okay. So the bottom line to the question of why is that everything wants to release any stored potential energy it has if it can. And it can do that by converting that energy into kinetic energy, which is for the purposes of atoms and molecules. When we increase motion, we increase our temperature. So we release that energy as heat, essentially. And so for atoms, that means heat. Higher the temperature, the more individual atomic motion that we have. Lower the temperature, the less motion we have until we reach absolute zero, which is zero motion. You can't have negative motion. And so there is a floor to the temperature scale that we can't go below, because the temperature scale is just reflecting the amount of movement energy something has. When something stops moving, you can't go any lower. Did we talk about the Kelvin scale at all? The Kelvin temperature scale, where absolute zero is the lowest temperature you could have. And 0 Kelvin corresponds to negative 273.15 Celsius. Two of you guys were typing an answer, but you stopped while I kept talking. Couldn't remember if we talked about Kelvin before. But in any case. All right, so that's what we've got for energy. So heat energy in particular is one of the thermodynamic qualities of a reaction or a process, which is known as enthalpy. There's kind of a lot of jargon in this chapter, some named terms you're going to have to memorize. This is one of them. Enthalpy, also known as delta H, or the change in heat, change in enthalpy for a reaction or for a process. And for enthalpy, what we find, the way we've defined it, a negative value for enthalpy means that that process or that reaction is releasing heat. Whereas positive enthalpy, we're going to use for something which is absorbing heat. Okay, so negative would mean that my products are lower in heat energy than my reactants. So heat was released, and so since I'm lower, that became more negative. Positive value would mean that my products are higher in energy than my reactants. Therefore, I had a positive change in my delta H. Let's see, this is also, releasing heat is also called exothermic. And absorbing heat also called endothermic. And there's a couple of ways to know whether something absorbs or releases heat. Sometimes we'll just tell you, if I give you a reaction and then I give you a value for delta H, which is negative, then you would know, obviously, that it's exothermic, because that's by definition, negative enthalpy is exothermic. But there are a couple other things, if we're looking at some processes, that would make it kind of obvious, since we know that movement of atoms is heat, then anytime we go from a solid to a liquid, am I increasing the movement of my molecules or decreasing it? Liquids, these, hang on a second, if we look at our solid, our little pieces are all fixed in place and they can't move. That's why solids have a fixed shape. Whereas liquids, our little pieces, our little atoms or molecules can slide past one another, which is why liquids can flow, right? And then if going from liquid to a gas, we've got our little particles that are really far apart from one another and they're just zipping all over the place. So going from a solid to a liquid is going to increase the movement energy available or increase the heat available. So that would be a process of absorbing heat. Delta H is positive. I have to get warmer to go from a solid to a liquid. That also makes sense, because if you want to melt ice, you have to add heat. Exactly. Megan's right with me. And the same thing going from a liquid to a gas, if you want to evaporate water, you're going to have to add heat. And the backwards process will also make sense to you. Then if I'm going from a gas to a liquid or a liquid to a solid, I am losing movement energy. So these processes, my delta H would be negative. You guys following me here? Yay, okay. Let's check this out. First thing in class activity sheet 7, number 1, was to tell whether this process would absorb heat, that is be endothermic, or release heat, that is be exothermic. So snow forming in clouds, before you answer, ask yourself, what is this? Like, how would I write this chemical reaction? Snow forming in clouds. Snow is water, right? So I have water. In clouds, it's a liquid. There's little teeny liquid drops scattering light. And snow is a solid, right? It's frozen water. So going from a liquid to a solid must be exothermic. Perfect. All right. The reason that I have it, you go through this process, is because you guys are really tempted to say, oh, but it's cold in clouds, so that must be endothermic. It must be sucking all the heat out of it. No, 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 no. It's exothermic because I'm going from a liquid to a solid. Okay. Burning a candle. What do you think? Exothermic, endothermic? One vote for endo, one vote for exo. Here's the key. Look at the burning part. That's what I'm asking. Anything that ends in ing, that's what I'm asking about. Is the process of burning releasing heat to the surroundings? Or does it absorb heat to burn? What would happen if you put your hand by that? Yeah, it's releasing heat. You can feel the heat that it's releasing. The burning part, the wick part. Now here's where it gets confusing, because as it turns out, energy is always conserved. Energy is conserved. It's never created or destroyed, just like chemical atoms and molecules. It's always conserved. So if it's being released from one thing, that it's being absorbed by something else. So your system, which is the burning, the wick, is doing one thing, and your surroundings, which would be the air or your hand if you stuck it there, or the wax on the candle, might be doing the opposite, because the energy is being transferred from one to another. So Megan is exactly right. The wax melting is a process of wax going from a solid to a liquid, which you would hopefully all immediately recognize as an endothermic process, because I must be absorbing heat to go from a solid to a liquid. Perfect. But the burning process of the wick itself is exothermic. And this is just where some of that heat that's released goes into melting the wax. But look for the ing word. That's what I'm asking for. So burning is exothermic. Candle melting would be endothermic, but that's not what I asked about. Are you guys following me there? Okay. All right. Baking bread. Exo or endo? Endo. Perfect. You cannot bake bread without dumping heat into the system. You have to add heat to get it to bake. Okay. Water condensing on a cold drink. So condensation, we have water, which is vapor in the air, turning into water, which is liquid on the side of your cold drink. You guys all got it backwards. If you stop and you look, you're going from a gas to a liquid. Gas to a liquid, I must be releasing heat, right? Because a liquid is lower in energy than the gas. So the water that's condensing is releasing heat. So this is exothermic. It'll always help, if you can, to write out the process so you can really see what's going on. Again, this is a case of you've got a cold drink here with little ice cubes. And you've got water that hits the side of it and says, whoa, I just lost energy, and condenses into little droplets. Where does that energy go? It warms up the drink, melts that ice cube. If you let it sit for long enough, the ice will go from a solid to a liquid, and then the whole liquid will go from 0 degrees Celsius to 25 degrees Celsius, or room temperature. And so your surroundings in this case are the glass, but the system that I'm talking about, just what's going on the surface, we've got the gas from the air forms a liquid on the side. Is that a little bit less confusing now that I've explained that? Kind of like cup sweat, except it never goes from the water, like the water doesn't leak out of the cup. But yeah, that's one that's one way to look at it. Okay, excellent. Let's move on to entropy. Enthalpy is a pretty good prediction of whether a reaction will be favorable or not, whether it'll be spontaneous or not. Because if you release that potential energy as kinetic energy, then you know you're going downhill on the energy scheme. So often, if a reaction is exothermic, then it will be favorable. but not always. There's something else that contributes to whether or not a reaction will occur or not, and that is a measure of the disorder of the system. And this is really important because if enthalpy was all there was, then everything would want to be a solid and our whole world would just be a big solid blob. That there wouldn't be air, there wouldn't be water, there wouldn't be people, it would just all be solid. So disorder is what says, okay, well, why is it that anything would want to become a gas in the first place if this is an unfavorable process enthalpic-wise, okay? So disorder of the system, this is referred to as entropy, and it's known as delta S. And law of thermodynamics regarding entropy states that the entropy of the universe is always increasing. Enthalpy, energy is conserved, but entropy is always increasing. The disorder is always increasing. And just to confuse you guys, if entropy is positive, then the disorder is increasing. And if entropy is negative, then the disorder is decreasing. There's some double negatives here. Or the order is increasing if entropy is negative. And there are two ways, I mean, I could tell you if your delta S was positive or negative, but aside from that, there are two other ways that you can tell if disorder is increasing or decreasing. First is, again, look at what you know about going from a solid to a liquid and a gas and the makeup of the atoms and molecules in there. And you tell me, going from a solid to a liquid, would that increase disorder or decrease it? That would increase the disorder because here they're all very ordered and stacked and here they're actually moving around. So delta S is positive. I'm increasing my disorder going from a solid to a liquid, and the same thing from liquid to a gas. And again, if I'm going backwards from a gas to a liquid, I am decreasing my disorder. So my delta S is negative. Liquid to a solid, I'm decreasing my disorder or increasing my order. Delta S is negative. Does that make sense to you guys? Do you see how disorder increases going this direction, decreases going the other direction? Excellent. Okay. The other way that you're going to tell is by looking at the number of pieces, essentially, on each side of a chemical reaction. So if I have a chemical reaction that looks like this, which side of this reaction looks like it is more ordered or organized? Yeah, this product, right? This is, I have lots of different pieces here. If you look at, here's A, and here's B, and here's C, and they're all separate. And here I have a very specific pattern organization of the three. So here, my change in entropy is negative for this reaction as written because I have less disorder in my product than I did in my reactant. And Shauna is exactly right. All you have to do is count it up and say, let's see, I've got 1, 2, 3 molecules on the left, or 3 moles on the left, and 1 mole on the right. So going from 3 things to 1 thing, that is more ordered. You can just, once you balance the equation, you can just compare both sides and see which side has fewer things running around, essentially. So this is obviously a synthesis reaction. You're synthesizing something that's more complex than your original materials. So that's pretty clearly disorder is increasing. And then obviously if you looked at something like a decomposition reaction, AB goes to form A plus B, you could say, okay, I've got 1 mole on the left, 2 moles on the right, and falling apart. This would be forming more disorder. So now my delta S is positive. Everybody feel pretty good about those? Excellent. Okay, let's look pretty quickly at our in-class activity sheet and see if we can answer these questions. Okay, so part 2, predict whether the following reactions lead toward more order or more disorder. See, for this first one, I should balance it. I've got 4 phosphoruses. Gives me 4 phosphorus atoms. That gives me 6 magnesiums, 6 magnesiums. Okay, first reaction, more order, more disorder. Definitely more order. I've got 7 things going to form 2 things. So my delta S is negative, going towards more order. Let's see if I balance this. Gosh, I gave you space to balance here, but not here. I'm going to need a 3 here and a 2 there. Okay. What do you guys think about this one? More order, more disorder? More order. I'm going from 4 things to 2 things. Plus, these are all gases, and this is a liquid, so delta S is definitely negative, going towards more order. Okay, let's see. There's a combustion reaction. 5, 5. Okay, let's see. Gives me 10 hydrogens, 5 carbons. Then I've got 10 plus 5, 15 oxygens, minus 1, 14 oxygens. Okay, so that's balanced. Diana's totally on top of it. Definitely more disorder. I'm going from 8 molecules to 10. Plus, you see, one of these is a liquid and all of these are gases. So that definitely reinforces more disorder. And let's see, if I balance this guy, I'm going to need a 3 there. Oops. I'm going to have to double that so I can do that. So I can put a 6 there. And 3 and 2. Okay. What do you guys think? More disorder or more order? More disorder, definitely. Is that pretty easy to see? So disorder means my delta S is positive. I'm making more entropy. Excellent. Okay. There's no more questions on this. Then we can stop and move on to the next lecture. I think I balanced it. I might not have done a perfect job. 2 times 3 carbons gives me 6 carbons. Oh, my oxygens are way off. Hang on a second. 6 carbons, 10 hydrogens, 6 nitrogens, and then I have 18 O's. It's because I forgot there were O's here and here. So that's 5, and that's 12. So I have 17. Oh, crap. To make that 18, I'd have to put a half there, and now I have to double everything all over again. So that should be 4, 10, 12, 6, and 1. Good catch, Jay Houston. Excellent work. Doesn't change our answer though, right, in terms of entropy, but we're good. Okay, I'm going to stop this recording.